Hello, everyone. Welcome. Barbara, I'm just confirming if you can still hear and see me okay.
See, I sure can. I hope you can hear me.
Yes, great. Thank you. So thank you to everyone who's joined so far for today's live technical topic webinar. I hope you're all well. So my name is Riley and I assist in coordinating our various free webinars that we hold every month at EIT. You can find all of our upcoming and past webinars on the event page on our website. Before we get started today, you can turn off your notifications and sounds in the session by going to the settings or the cog symbol in the bottom right hand corner of your screen if you're on desktop, or you might need to go to the session menu if you're on mobile and go to the settings, and making sure that all the boxes are unticked under notification settings. That will make sure that you won't get any sounds or pop-ups during the session, which can be a little bit annoying. So today's session is learning how to learn for engineering professionals. So that's our topic for today. And our presenter is Barbara Oakley, who is a professor of engineering at Oakland University in Michigan. You might know her through a popular online course, Learning How to Learn, which I guess is the basis of this short 1 hour webinar today. We like to keep these webinars as interactive as possible, so please use the chat box if you have any questions or thoughts you'd like to share during the session. I'll be active in the chat box so I can answer any non-academic questions for you. So these webinars are recorded and you will receive a copy of the PDF slides and a link to the recording in an email within the next 2 business days. We also provide a free digital certificate of attendance, so there will be a link and a QR code that I'll provide at the end of the session in which you can fill out a short form or survey and you'll receive a certificate of attendance within the next business day. And if we have some time at the end, we'll also hold a Q&A session, which you can ask any questions for Barbara or I. So just to give you a brief introduction to EIT if you're not already familiar with us. So we're an engineering education provider. We have courses ranging from advanced diplomas, and we have courses in the higher education sector, such as bachelor's and master's degrees, and recently a Doctor of Engineering degree. We also have a range of short courses that we call Professional Certificate of Competencies. We have industry-oriented programs, so we have a range of industry experts that ensure our courses are relevant with the current industry, as well as we have Australian accredited education for our vocational and higher education degrees. And we also hold international recognition for some of our courses under the Dublin, Sydney or Washington Accord with Engineers Australia. We also have industry experienced lecturers, so not only those who are experienced in academia, but those who actually have real world experience that can connect the learnings to practical situations. We also have a unique delivery model. We have on-campus courses for bachelor's, master's and our doctorate program, but all of our courses are delivered online as well. And that includes the use of live and interactive webinars, similar to the one that you're in today. Our expert lecturers, we have dedicated learning support for all of our students at EIT, and we also have state-of-the-art technologies such as hands-on workshops, remote labs, and simulation software. Now, I'll hand over now to Barbara to briefly introduce herself, and she will be running the session today. So thank you very much, Barbara. Over to you.
Okay, well, thank you so much. And let's go ahead and get started, Riley. It's so nice to be here for EIT. It's just a great company, and it provides some really terrific insights and educational opportunities for people around the world. And it's a special pleasure for me as an engineer to be sharing here today. So I'd like to introduce our talk. This fellow here, his name is Julius Jaego, and he is one of my favorite athletes of all time, and I will explain why later on. So I should give you a little bit of a sense of my own background. I grew up moving all over the United States. So by the time I was about 15 years old, I'd lived in 10 different places. The thing is, math is a very sequential subject. And when I was 7 years old, we moved from Texas to Massachusetts. They were suddenly far ahead of me in the multiplication tables. I didn't like math anyway. And so I just said, well, I don't have the math gene. And I flunked my way through elementary, middle, and high school math and science, which really is ironic since I am speaking with you today as a distinguished professor of engineering. And I'm the real deal. I publish in top journals, and I'm a fellow of top engineering societies. So one day, one of my students found out about my sordid past as a math flunky, and he asked me how I changed my brain. And I thought about it. I mean, I was this little girl, and I really like this picture of me because it's the last cute picture of me. But I loved animals and knitting and weaving and all that kind of thing. So since I knew I could never grow up and do anything analytical or technical, I thought, well, why don't I try and learn another language? And of course, I know many of you are bilingual, but I certainly was not. And my family was monolingual, and you can guess what language we spoke at home. So I found out, I couldn't afford to go to college and study a language, but there was one way I could learn a new language and actually get paid for it. And that was to join the Army. So you see me there looking very nervous, about to throw a grenade. And if you knew how clumsy I actually am, you would know why I look so nervous. But I did learn another language. I learned Russian. I ended up working out on Soviet trawlers up on the Bering Sea. And I just loved seeing the world through new perspectives and with a sense of adventure. So I also ended up working at the South Pole Station in Antarctica, and that is where I met my husband. So I often say I had to go to the end of the earth to meet that man. But what I found, to my surprise, was that I'd done everything people said. I followed my passion. And what I did was I followed that passion right into a small career box because hardly anybody was looking to hire someone whose sole professional expertise was the ability to speak Russian. So I hadn't really, I thought about following my passion, but I hadn't thought about broadening my passion. Russian is any language is great to learn along with other things. So I, at age 26, I decided to try and see if I could learn in math and science. After all, my friends were actually getting great jobs in that area, and that was as true 30 years ago as it is today. Technology and engineering is a fantastic field. But as I was beginning to learn, I realized that it was really difficult. And if I'd known then what I know now about learning, I could have made it so much easier on myself. So neuroscience has made tremendous advances in the last years, and cognitive psychology. And there's these tremendous insights that are often unknown or little known. And so what I want to do today is share with you some of the best insights on learning that are relevant for we as engineers. And to begin with, we should look inside the human brain. And of course, we know the brain is incredibly complicated, but we can focus on a single thing in the brain that will really help us to better understand how the brain operates. And that single thing we should look at is the brain's fundamental building block, or at least one of them, and that's the neuron. There's 86 billion of them in the brain, and I know what you're thinking. You're thinking this is where she gets to the super boring scientific part, so we have to spice it up just a little bit. And we'll use a metaphor to better understand just the brief essence of the most important things that neurons do. And our metaphor is a space alien. So the space alien has legs. So you can see it's got 3 legs down below. Those are called dendrites on a real neuron. So here's the dendrites. And it's got these little toes on it. These toes are called dendritic spines. And as you will see, they are tremendously important in learning. And then our space alien has an arm that reaches upwards. That's called an axon. And what neurons do is quite simple. They reach out with their arm and they more or less tickle the toe of an adjoining neuron. That's their main claim to fame. That's what they do. They reach out, and what they're really doing is sending an electrical signal, actually hops this little gap with neurotransmitters from neuron to neuron. And when you are learning something, what you're actually doing is creating sets of links between neurons in long-term memory. So whether you're learning to take a derivative in math, or how to conjugate a verb when you're learning a language, doing a pirouette, or learning a musical instrument, whatever you are learning, if you've learned it, you are making links in long-term memory. One of the worst things that has come out of psychology in the past, and education in the past decades, has been this idea that you don't need to remember things, you can always look it up. That's simply not true. Would I be able to speak Spanish if I used Google Translate to always look it up? Of course not. And it's similar for learning in engineering. If you are always looking up those equations and so forth, you don't have that essence of the central ideas in your mind. So as students practice, they are strengthening their connections. And the more they practice, the more, of course, those connections get strengthened. So, as students are practicing, they're actually it's almost like they're strengthening these sets of neural links that are in some sense kind of like a big chain. And that set of links like that is actually what you have learned. So that topic, that technique, that translation of a verb, or the grammatical structure, or the geometric distribution and how to use it. Whatever you're learning, if you practice with it and know it well, you are actually creating these nice solid sets of links in long-term memory. So this brings me to what probably one of the biggest and most important ideas that I could share with you today. And that is, what is the most powerful way to learn? I'm going to give you 4 different possibilities. And what I'd like you to do is just hold in mind which one you think is the most efficient way to learn. Is it rereading? I mean, after all, rereading is practicing. It's going over the material. Is it highlighting or underlining? So, I mean, you're using your motor neurons to actually move that pencil on the page. So that may be helping to reinforce the ideas that are going into your brain. Is it something called retrieval practice or recall? So in other words, using something like a flashcard, so you retrieve the ideas from your own mind. Or is it what's called a concept map, where you write down the different concepts, the key ideas, and then connect them together? So we've got 4 different ideas, and which one did you pick? Let's see if it's right. The answer is retrieval practice. It is by far, as it turns out, the best way to learn. And why is this? Retrieval practice is, for example, using a flashcard to see, let's see, the word fog in Russian is tuman. Okay, let's check the back of the card. What I'm doing is I am seeing if I can retrieve it from my own mind before I check the back of the card. That retrieval is actually strengthening the sets of neurons. And I'll show you what I mean. You initially learn something, there's a weak pattern, but then once you retrieve it and retrieve it and retrieve it again, you are actually strengthening those neurons, that neural set of connections. And that is the best way to learn, not through concept mapping or underlining or rereading. In fact, this is by far superior. And it isn't just sitting there and memorizing things. Retrieval practice, as it turns out, helps build student understanding. So you're not just thinking about, okay, what is this topic? You're trying to actually understand it as you are trying to recollect it. So research has shown that, especially when it comes to scientific ideas, as people retrieve, say they read a page in a book, then look away, see if they can remember or retrieve those key ideas, they will understand those ideas even better. So if we're, the thing is though, with a lot of students, they get very busy. I know my university, for example, has a commuter school where people will often work a job or 2 jobs, and then they're trying to take a full load of classes. And what can happen is they can even understand something that you say in class, but then they go away and they don't have time to review anything for 2 or 3 weeks. Well, in the meantime, what happens is, let's see, this is not animating properly. Let's try this one again because it's one of my very favorites. There we go. So, so what happens is those little synaptic janitors just sweep away the dendritic spines that are not being used. So this indeed is why it's so important to repeat and to practice with the information that you're learning. And so it's a little like this. When you're learning during the day, dendritic spines pop out. But what's really important though is that at night, let's see if this can go here. Come here. At night, that's when the practice actually occurs. So sleep is an incredibly important part of effective learning. That's when the brain is practicing. And that's why students, they of course should study during the day, but right before they go to sleep at night, they should review what they really want their brain to be thinking about or practicing with during sleep. And that will actually allow the brain to practice more during sleep and reinforce that learning. And we can see this with light microscopy images. You can see here's an image before learning. This is a dendrite with the little dendritic spines. You're all budding neuroscientists now. And so this is an image of a living neuron before learning and before sleep. And this is the same exact living neuron after learning and after sleep. Wherever you see these little blue triangles, that's where a new dendritic spine has emerged and strengthened because it has been practicing during that sleep period. So This, again, is why it's so important to space out your learning. If a student has, say, 5 hours during a week to practice with materials, their tendency is to say, well, I'm going to cram all my study on Saturday, say. Well, or maybe Friday night, or maybe Sunday night right before the test. But if they space out their learning, so it's 1 hour per day over 5 days, instead of 5 hours all in one day, they will learn much more efficiently by spacing things out. This latter way of learning actually creates weak sets of links because they haven't had the opportunity to also be strengthened, not only during the day's practice, but during the night's sleep. So spacing out, spaced repetition in learning is incredibly effective. And it's a little like building a brick wall. You lay a layer of bricks, lay some mortar bricks, but before you go too high, you want to let that mortar dry. If you don't do that, if you don't take time with learning, your wall will look something like this, a very, very poor foundation for learning. So it's a little bit like athletics. We know this weightlifter did not sit down the night before a big meet and say, oh, gee, I'm going to build this muscular structure. It takes time to build muscular structure. And similarly, it takes time to build neural structure. But students often simply don't understand because they can't see inside people's brains like they can looking at a person, an athlete. So learning it involves a number of different kinds of ideas. It's a little like baking a cake. A cake has eggs and frosting and, flour and all sorts of different ingredients. Learning has lots of ingredients too. One of the most important, well, I suppose you'd call it an anti-ingredient to learning, something that impedes learning a great deal, and I'd say it's the biggest impediment to learning, is procrastination. And procrastination occurs because, well, when people even just think about something they don't like or don't want to do, it activates a portion of the brain that experiences pain. So the brain kind of does this sort of thing. Let's say that your students are sitting down to do their vector calculus, and they get this kind of unpleasant feeling because they don't want to do it. And so they turn their attention to something more pleasant. The result, they feel happier almost instantly. They do this once, do it twice, no big deal. Do it very often, and it can have profound effects on their life because they can think that they can't do something when actually they've just waited until that last possible second. And few people can work under those kinds of stressful conditions. So the biggest, bestest solution to procrastination, in my experience, is the Pomodoro Technique. This technique was invented by an Italian, Francesco Cedillo, in the 1980s. And we now know from neuroscience today that it's a technique that's so simple, but uses all sorts of insights from neuroscience. And that's why it's so effective. There's over 3 million students in learning how to learn. If I could tell you one single thing that people have found most effective in that course, it is the Pomodoro Technique. So I strongly and highly recommend it. And if you aren't using it, or if you knew about it but kind of forgot using it, you might want to think about it and think about teaching your own students. So to do this technique, you just turn off all distractions. So nothing popping up on your computer, no cell phones ringing or anything like that. Good luck if you have a 2-year-old at home, but mostly you can get away from distractions. Sometimes I will put an enormous set of earphones on my head to just block out sound, and that works great. But then you set a timer, any timer, for 25 minutes, and you focus as effectively as you can for those 25 minutes. Now, if you're like me, sometimes I'll be, I know I'm procrastinating. I'll set a timer and I start working, and I worked so hard and I know I'm almost done with the Pomodoro, and I look up at the timer and I've just done 3 minutes of the Pomodoro, and my mind screams, I cannot do 22 more minutes. But I just let that thought go right on by, kind of like a Zen thing, return my focus to my work, because anybody really can do 25 minutes. But at the end comes the most important part, and that is the reward. And this reward is like you can do 5 minutes of listening to your favorite song, or maybe going and having a cup of tea, walking around a little bit, doing something mentally relaxing. If you go to your cell phone and check to see if you have messages, guess what? If you have a message, you're going to be returning to your focus as you answer the message, and you're not getting that relaxing, diffuse mode break. So try to do something that allows your brain to truly rest and offload the new information that has been learned. So we've talked a little bit about the importance of storing information in long-term memory as sets of links. And what we haven't really discussed, though, is working memory, which is in the prefrontal cortex. I like to model working memory as like this octopus that only has 4 arms, so it's like a quadrupus, because the reality is your conscious awareness can only hold so much stuff. And generally they used to think it was 7 pieces of information that you could hold, but now they think it's more like 4. And what this octopus of working memory can do is reach into long-term memory and grab sets of links about what you've learned. So it can be anything, a technique for doing something, some facts, whatever you've learned. Let's say you've learned a piece of music on the guitar. If it's a short piece of music, it may be like a smaller set of links. If it's a long song, you've grown it into being something that's really a much larger set of links. So those sets of links and that working memory octopus, when you are learning something, what it's doing is it's trying to create those sets of links so that it can store them in long-term memory. And then later, what your working memory can do when you need those sets of links or those ideas, it can easily pull those ideas to mind. So this is part of why students practice and become familiar with and really get to know the material so that later on tests they can pull it instantly to mind. Now this brings me to our younger daughter, Rachel. Rachel is going to model what it was like for her when she was learning to back up a car. Now, if you think about it, backing up a car is a really complicated sort of thing to do. And when you're first learning how to back up that car, it's really complicated. Watch Rachel as her little face is like trying to grapple with backing up the car. Do I look in the side mirror, or which side mirror, or the central mirror, or do I just turn around and look? And then of course off she goes into the ditch. This is what it was like for her when she was first learning to back up a car. And so in essence, what was really going on was her working memory was just filled. It was trying to take in all this information, and she had what's called a heavy cognitive load. And she didn't have any arms on her octopus available for doing anything else. Don't try talking to a person who's trying to learn to back up, because they're totally preoccupied. But once she learned how to back up the car, it was easy. All she had to do was just think, oh, I want to back up the car. She could pull this set of links to mind, and voila, she could back up the car. So she had what's called a light cognitive load, and she has arms available on her working memory octopus for other ideas like, okay, oh, is my seatbelt fastened, or what's playing on the radio, these kinds of things. Although I've modeled this for backing up a car, it's really similar. We're creating sets of links even when we're learning complicated mathematical topics. So what we really want is we want our students to have practiced with the key idea of the key elements of what we want them to learn, so that when we might be testing them, and testing incidentally is very powerful for learning, they can just kind of go, oh yeah, this clever professor is just asking me to kind of think about how this relates to that, relates to this, and voila, they're able to solve tests, the questions we put to them on tests. And again, testing is actually a really good way to learn material. So when people are saying, oh, we should get rid of tests and so forth, no, tests they're invaluable for learning. 1 hour spent testing as opposed to 1 hour spent studying, you will learn far more during the test. But let's say that a student doesn't use retrieval practice when they're studying. They put a lot of time in, but they're rereading and underlining and maybe concept mapping. What can happen is they can sit down to the test, and as they sit down, that's the first time they test and try to retrieve how to do the information, the problems, and they don't know how to do it. So they think, well, when I was sitting in front of the book, I could do it. So I must just suffer from test anxiety, because we have not taught them what good learning actually involves. So it's really important to not only allow students, or it's very important to teach students how to learn effectively. And oftentimes we're so focused on, on teaching them the subject that we don't do that little bit of ancillary help that allows them to learn the subject more effectively and learn how to learn more effectively. So for example, we often give a gigantic test at the end of the semester, or maybe a midterm and a final, when frequent smaller tests can actually be more effective because they'll help prevent procrastination, and they force students to kind of keep up with the material. And of course, it's okay to allow students to try to avoid having open book tests. We've been encouraged for decades to use open book kinds of tests. That's really not the best way to go as far as neuroscience is informing us, because when you have an open book test, students will procrastinate. They'll just kind of think that they can figure it out on the fly during the test. They won't study as hard. If you have a closed book test, you can make this test simpler, and it also helps them get those key ideas into their heads. And really, that's where it's all at. So working memory capacities in your students often vary. As I mentioned, typically people will have 4 arms on their attentional octopus, but some people have 3, lesser capacity working memory. Others have a lot of, really tremendous number of arms on their working memory octopus. But as you'll see, having a lot may make you a faster learner, but it doesn't necessarily make you a better learner. Having fewer arms may make you a slower learner, but it actually can help you sometimes be a better learner. And what I'm really talking about is, Those with a large capacity working memory, they're kind of like race car learners. Those who have fewer arms on their working capacity memory are more like hikers. But race cars, everything goes by in a blur. For hikers, they can reach out, they can touch the leaves on the trees, smell the pine in the air, see the little rabbit trails. They have a completely different learning experience, and in some ways, it's far richer and deeper. My hero in science, Santiago Ramon y Cajal, was a terrible learner growing up. He was a total hiker learner. And he was kicked out of elementary schools, just couldn't learn very well, had real struggles. And he went on to win the Nobel Prize and is now considered the father of modern neuroscience. He was asked, how did you do this? I mean, what was your special sauce? And he said, number one, I was persistent. So he would practice and create those sets of links. But number two, he was flexible. When the data told him he was wrong, he could change his mind. A lot of the race car learners, and in fact, research is now beginning to reveal that those who learn very quickly are often far less flexible. So when his data told him he was wrong, he could come up with a new hypothesis. When the geniuses he worked with, as he said, when their hypothesis was wrong, they would simply use their intellect to find a way to justify why they must have been right after all, no matter how wrong they actually were. So if you or your students are no geniuses and they're hiker learners, rejoice, because sometimes they can do things that geniuses cannot. Now, for these slower type learners, and they can be slower types because they've got a smaller capacity working memory like me, or they can have differences in their hippocampal functioning, differences in the bath of neurochemicals that washes away dendrites. Whatever their reason for learning more slowly, they can learn more deeply. And the way to facilitate their learning, though, is to scaffold their instruction. In other words, break that material up into smaller chunks so that if they've only got 3 arms, for example, on their attentional octopus, it's a small enough chunk that they can get that in and get it into long-term memory. And they will need more practice, but once they've got those ideas in long-term memory, they can merge them together and really deal with very complicated ideas and quite efficiently and flexibly. So this brings me back to my dear Julius Yego, my favorite brilliant genius athlete. And Julius is from Kenya. And if you know anything about Kenya, you know that they are very famous for their long distance runners. And if you look at Julius's arms, he does not look like a long distance runner. And in fact, he always wanted to learn to throw the javelin. But there were no javelin throwing coaches in all of Kenya, and he couldn't afford to go and study overseas. So he began watching YouTube videos. And 98% of the time, simply by watching YouTube videos and then going out and practicing, watching, practicing, he became the world champion at the javelin. So I think there's a lot of lessons for us out of that. First of all, you can learn a lot online and a lot more than people often give things credit for. But also, Julius gives us a good sense of what is really going on when you're listening to a lecture versus practicing. Now, for thousands of years, people thought that the only way you actually learned was to sit and listen to a lecture. And so you'd bring students to school and they'd listen to lectures for 8 hours in a day. And then about 50 years ago, people started questioning this. They said, look, it's really long periods of lecture don't work that well. So what students learn better with is active learning, where they're actually working themselves with the material. And so let's go to active learning. Let's always have students do things. I mean, when you really think about it, that doesn't make sense, because how can students just always be doing something? I mean, they have to be learning part of the time. I couldn't just turn you loose with my slides and say, figure it out for yourself. I mean, you have to have some sort of initial guidance in order to try to really help people learn effectively. Should it be something like a lot of lecture and maybe a little active learning? Or should it be maybe something with a little lecture, a lot of active learning, or maybe a mixture that's pretty even of lecture and active learning? Well, we don't know. All we know is that this mixture of lecture with active learning is incredibly effective. This mixture is called direct instruction. People will sometimes erroneously say, oh, direct instruction, that means just teaching, that means lecturing. No, it doesn't. Direct instruction is that mixture of lecture or explicit instruction with active learning. It is so powerful, and it's been shown to be that. In fact, one of the world's largest educational studies ever performed was conducted over 9 years, and it involved hundreds of thousands of school children. And it was called Project Follow Through, and the results tested constructivist approaches, self-esteem approaches, a variety of different approaches, about 10 altogether. And what they found in the end was direct instruction was so incredibly far ahead of any other methodology for teaching that they actually did not publish the study as a consequence. Why? Because, I mean, think about it. 9 of the groups that you're studying get only one of them won. The other 9 are like, no, we're out here, we're important. And so between all 9 groups, the results were just suppressed and not published. But it's now becoming very nicely and widely known that direct instruction is, think about it. You give a little bit of instructional insight, and then students do some stuff on their own. That's the best way for students to learn. And that indeed is how Julius was learning. He would sit there and he would kind of watch the videos, pay attention. So he's listening to explicit lecture, and then he is going out and actively practicing with the material. So what he's doing is simply lecture and active learning. Lecture mixed with active learning. This back and forth was part of the magic that led him to becoming a world champion. But what is actually going on in the brain when you're doing this mixture of direct instruction? It's fascinating to see. So remember before how I talked about sort of a set of links that we want to put into long-term memory in order to be able to learn material well. But what I didn't tell you was there's 2 different ways that those sets of links can be deposited. The first way takes information from working memory through the declarative system of the hippocampus and on into long-term memory. The second is procedural learning. That goes right through the basal ganglia and deposits links in long-term memory. You might think, who cares which system is used to deposit sets of links in long-term memory? We all care, because these different links have different characteristics to them, and we need both in order to be able to learn well. So declarative learning, how can we help with that? Well, both declarative and procedural are helped with retrieval practice. We've mentioned that before. Spaced repetition helps with both ways of learning. Explanation helps declarative. Varied practice itself, that's mostly procedural. If you have rapid feedback, procedural. Delayed feedback, like you get the report back days later, that's declarative. And lastly, interleaving really helps support procedural learning. So the thing is with interleaving, if you have, let's say you have geometric distribution, binomial distribution, and negative binomial distribution. Our normal way of teaching is like 10 problems of, geometric, and then 10 more of binomial, 10 more of, but the reality is once students have done it 2 or 3 times, they're just copying. They're not really thinking actively about the material. So once they've got the essence of the idea down, you want to interleave, mix up what they're practicing with. And this is a powerful way for that procedural system to actually learn the material better. Because the procedural system, as it turns out, is a system that is very, it allows students to think about things without even thinking about them, to do things without thinking about them. So if you have backed up a car enough times, you've learned that through the procedural system, and you can back up the car. You do the multiplication tables enough times, you can do fractions and see relationships when you're doing algebra that you don't even have to think about, because you have a natural intuition, because you've laid sets of links in long-term memory, also via the extra practice through that basal ganglia procedural system. So this procedural learning is extraordinarily important. It's what gives you the intuition to do well on problems in, say, in engineering. So students will often make the mistake, for example, of just practicing, or they'll do a homework problem and turn it in. If it's a key homework problem, they should practice retrieving how to do those key ideas from long-term memory over and over again until it's almost like a song that can flow through their mind when they see that problem. This kind of thing can help them develop an intuition. They can look at problems and see intuitively how to begin to solve them. And that is the magic of that incredibly complex pattern recognition system of the procedural system. So just a last bit on interleaving. Normally we hand out assignments, kind of topic 7, give them a bunch of problems. Instead, try to interleave with some other kind of related topics if you can, so that students don't just encounter interleaved material on the final exam, but even in the homework problems. So when students are learning, they often, we want them as much as possible to learn declaratively and procedurally. But those who tend towards dyslexia, they can prefer to learn more declaratively. Those who tend more towards the autistic spectrum can prefer to learn procedurally. And there's nothing wrong with that. So I think one thing that is really kind of important is traditional methods of teaching have long been disparaged as sort of drill leads to kill in the US and in Western countries. But the reality is that drill can actually lead to skill when cleverly done. So there's so much that I have covered here today. I know that you might think, well, you didn't give us enough time to actually practice all that was taught today. But if you would, please be like Julius Yigo and go forth, take these ideas that you've learned online and use them to practice with, and you will see that learning will be improved. And with that, I would like to stop, and I think we have a few minutes for questions.
Thanks, Barbara. That was lovely. That was very insightful. I'll just put the slides back on. So before we get into the Q&A, usually I'll have some upcoming webinars on this slide, but that was our last webinar of the year. But we do have webinars planned starting late January, but for now we'll take a little bit of a break, and you can always check our events page if you would like to attend a upcoming webinar. And I've just posted our course schedule. So we have courses starting in mid-January. As I mentioned at the beginning of this webinar, as you can see, we have a range of engineering courses, and these are our most upcoming. And we also have our bachelor degrees starting in February, and our 4 main fields that we cover are civil engineering, electrical, mechanical, and industrial automation engineering. So if you would like to see any of our courses, or if you are interested in having a look, I would recommend going to our website and looking at the schedule page, which you can see all of our upcoming courses. Now, as mentioned, you will receive a certificate of attendance if you complete the form that's linked on the screen. So I will post the link in the chat box, or if you have your phone on you, maybe you can scan the QR code on the screen. But otherwise, I've just posted the link to the form in the chat box. So if you would like to receive the certificate of attendance for this session, please go ahead and click the link or scan the QR code for your certificate of attendance. And I will be planning on sending those out by the end of the day. Now, before we wrap up the session, we'd like to do a short Q&A. So I think there's already been a few questions coming through the chat box, Barbara. I think the first one I saw was from Ilya. They've said, Dr. Oakley, I'm currently doing a PhD research into effective teaching of conceptual modeling in information systems. What good references may you recommend to further read into the topics that you've just discussed, in particular the process of working long-term memories in the context of learning declarative and procedural would be interesting. Comparison of direct instruction with other methods as well. Thanks.
Okay, I think I've got these, so I'll try to answer as many as I possibly can here. So for this question, if you might take a look, there's a book called Uncommon Sense Teaching, and it's got like a zillion references. And so if you could take a look at that book, it has a careful discussion of all of those topics, and it also has a very nice set of references at the end. I would also like to point you towards, let's see, I've got an online course called Learning or Uncommon Sense Teaching as well. It is on Coursera. It's free, and so it covers a lot of these ideas as well. If you wanted, You know what I could do? I could be wicked. Riley, how wicked would you like me to be? I've got a 1 minute and 45-second sort of introduction to the course, and it's pretty funny. But if you'd prefer that I ask question or answer questions, I can do that too. Or instead.
Looks like we've only got a few minutes left, so it might be better if we just get through a few questions.
Okay.
I think there will be some more popping through, but if you do need to provide any links or anything to any of the questions, just feel free to put them in the chat box.
Okay. So can you, let's see, can you explain the difference between declarative and procedural learning? Is it about lectures and practice? So your brain has a little part in the very back that says, do I do this a lot? You know, am I always like punctuating a sentence with a capital at the beginning of a word? Do I keep doing that? Oh, really? I'll create a set of links that's part of what I need to do for punctuation. Do I drive home the same way every day? Oh, I'll create a set of links about that. So that is how you are learning procedurally. It's stuff that you do a lot and you do it over and over again. And it's also things that you're like, when you're learning your native language, you are learning that with your procedural system. So you're hearing all these words and you're hearing how they get pieced together. And your procedural system is very much, in fact, artificial intelligence is sort of modeled after that procedural system. It's a deep network, and that network is learning all that information by all the information that you're inputting into your, in other words, that you're experiencing. So, declarative learning through the hippocampus is more like I explain this, like what I'm explaining to you right now is all sequential sets of ideas, and that's what the hippocampus, it's like that's what you're learning. You're conscious of what that learning is. You're not conscious of what you're learning procedurally. So it is about lectures and practice, but it's much more. And if you might take a look, so both the book Uncommon Sense Teaching and the massive open online course Uncommon Sense Teaching cover somewhat similar material, but with the course, which again is free, you can see things moving. And so you can see how that procedural system is learning, how that hippocampal declarative system is learning. What do you suggest for a good method to take notes that will not be time consuming and will make it easy to follow? What a great question. So the simplest way is what I call a modified Cornell system. And all I do is I draw I'll take a piece of paper and, well, this is all busy paper stuff. Where is it? Let's see if I can find a piece of paper, but of course, when I'm looking for things that are always gone. Okay, so there we go. Okay, so then I take and I'm going to draw a line. Hopefully you can see that about a third of the way over. I take my notes on this side. Then afterwards, I note down key ideas from those notes on this side. Then I can cover up my notes, look at the key ideas, and see if I can retrieve those key ideas. Notes are really, they're effective because they are tools that allow for retrieval practice. So let's see, what do you think of Zettelkasten technique? That's a new one on me. I'll have to go look that up. So sorry, I thought I knew most things I usually know, but that's a new one. Okay, thank you, Dr. Oakley. I've been following you for several years. I'm an FYE instructor, so learning how to learn has been invaluable. Oh, that's so good to hear. Well, thank you, Sandra. this is all about helping students to learn. There should be a recording that's available. Where's the link should be made available. If you really would prefer to have the PowerPoint over the PDF, I'm glad to share that. I can send that to Riley. And do you have any suggestions outside of the Pomodoro technique? It sometimes takes 30 minutes to get into a state of sufficient flow to tackle a tricky proof. You know, what I do is I do a preliminary Pomodoro, knowing that I'm not probably going to be that effective. It usually, when I'm starting to work on something new, it can actually take me several days of, you know, do a Pomodoro the first day and it's really grudging. And then the next day and it's still pretty grudging. And then the third day I'm like, well, you know, maybe I'll do a second Pomodoro. And then, you know, so sometimes when I'm tackling something really new, it takes me a few days to really get into it. So let's see, Riley has done such a fantastic job in organizing this. So let's see, I'm a late diagnosed female ADHDer in engineering school. Okay. Do you recommend I read Uncommon Sense Teaching first or Learn Like a Pro? Read Learn Like a Pro. Learn Like a Pro is like super condensed and it's really new. Mind for Numbers is autobiographical, so it's not as condensed. Even though it's older, all the ideas are still right there. One thing I want to say for ADHD, number one, use the Pomodoro technique and also set a timer for the breaks. Be really, really careful to try your very best to get distractions out of the way. Those big headphones, you know, I use like their 31 decibel super duper, you know, highest quality. I don't use the noise canceling earphones because they're not powerful enough. So I just use like the biggest ones I can recommend. And that actually trains my brain so that when I put them on, I concentrate better. So let's see. Oh, thank you very much, John Paulo. And thank you, yeah, okay. And thank you, everyone. This is, I'm so glad this was useful for you. Let's see, any more? Let's see, Modified Cornell. Okay, good. I've just graduated secondary. Oh, well, I'm so glad. If you take a look at the Uncommon Sense Teaching MOOC, Massive Open Online Course on Coursera, you will love it because it has all this stuff. And again, it's free. Just ignore the stuff where they say, well, if you'd like to get a certificate, because you can just take it all. In any case, okay, it looks like I've gone through the questions. So thank you. It's just been a real pleasure. EIT is awesome. I just only wish I was back in Perth to give the talk from there because it's my favorite city in the world. But I think many of you live in a lot of places that I would love to visit. So hopefully I will see you on one of my travels.
Yes. Well, thanks, Barbara. Thanks for going through all of those questions. And thank you to everyone who attended the webinar today. We really appreciate you joining us. And yeah, I will send out the email later today with the PDF slides and the recording. And if you filled out the form for a certificate of attendance, I'll also send that out in the next few hours. And thank you very much. Have a good rest of your day wherever you are. And we hope to see you again in the future. And thanks, Barbara. Thanks again.
Okay, thanks, James. Thank you all. I hope to see you again.